elements. Where do we leave off? Looking at hybridization, right? So, this.
Okay.
Given the problems of hybridization, let's look at let's look at beryllium dichloride and see if we land where we should. Of electrons in a linear arrangement of 3 atoms. Two regions of valence electron density in beryllium-2 molecule that corresponds to the 2 covalent beryllium to chlorine bonds. To accommodate these 2 electron domains, 2 of the beryllium atom's 4 valence orbitals will mix to yield 2 hybrid orbitals. This hybridization process involves mixing orbitals. This hybridization process involves mixing of valence s orbital with one of the valence p or 2p, right? But in order for this to attain the proper shape, right? I need it to essentially do this. I need a lobe here, and I need a lobe here, so they can get as far away from each other as they can in repulsion. And of course, I need that then to interact with chlorine. So this is a hybrid form. Normally, I mean, if it's just hanging out here in 2s, then I've got 2 atoms that are just in this spherical shape, and that's all there is. And then to have that come in and interact with chlorine, I'd have to have them both in the, the shape necessarily has to change. So this is going to hybridize. So we're going to go from 2s, and we're going to borrow one of these 2p's, right? So I'll still have 2p's unhybridized and empty. And then I will also have 2 of these 2sp. Oh, I'm sorry, just sp. These will each have 1, right? And so then the shape of these will be like this, which will allow me bond the way I need to with chlorine. Okay.
And the 2 electrons that go to the sp comes from the 2s.
They come from the 2s.
They just get the form of...
Yeah, they've got to jump up the partial energy level into this hybrid shape in order to give the optimal configuration with them on opposite ends.
Okay.
Otherwise, they'd both be in tight and that spherical, right? And that making slight assumptions, but essentially you're looking at too many electrons in too tight of a space. It would require too much energy, and so it's less energy to go ahead and hybridize than it would be to stick all those in one little spot. All right. What else are we doing with this? Means of review and making sure we understand this hybridization stuff. So that was a simple SP. Let's go ahead and let's do some SP2. All right, for SP2, I want to do. Your book gives you an example. It is BH3. Okay, so boron is atomic number 5. right? So I've got one S2, and I've got 2S2, and then I've got 2P1, right? So when I do my diagram here, here's my 2S, I got one up, I got one down, and I come here to my 2P, and I've got one up, right? Okay, so now we need to hybridize. We're going to make 3 orbitals, right? So I'm going to use my 2s, and I'm going to use 2 of my p orbitals for this. So that's going to give me my 2p. This is my sp2, sp2, sp2. That's going to stick 1 in each one of these, right? And so, and then there's nothing anywhere else as far as the valence. What shape is this going to be?
The double shape?
No. Oh, I'm sorry.
The molecular shape?
Yeah, what's the molecular shape here?
Is it tetrahedral?
Not a tetrahedral. Because look at how many domains I have. I only have 3.
I forgot the name, I'll have to check.
That's okay.
It's the trigonal plane.
Trigonal planar, that's right. So it's going to be like this. Right, and then it can go ahead and it can bond with hydrogen. Okay, good. sp3 hybridization. What shape is this going to yield?
Now the tetrahedral.
Tetrahedral, yeah. Let's see. Let's use CH4. CH4 will work great. Okay. So carbon, atomic number 6, right? So I got my 1s. I've got my 2s. And I've got my 2p. So I'm going to form here
sp3?
sp3, right? So we're going to, for this, we're going to use all 3 of these plus 1 of these, right? So we're going to have 4 of these.
The maximum that you can form is sp3?
If we're using s's and p's.
Oh, okay. We can do
Well, I'm sorry, is that? Yes, that is correct. But we can, you actually can go into the D's and then get certain, that's where we'll get some of our other crazier shapes, right? Okay, so sp3, you have 1, 2, 3, 4 of these, right? And so what shape?
It's the tetrahedral.
You know how to draw it.
Yeah, it's the into out of the
Right, something like that. Okay. All right. Let's go ahead and let's look at some of these others. S sp3 sp3d. Alright, for this one, let's do PCl5. Okay, so phosphorus, what's our atomic number?
15.
15. Okay, so we got 1s, we got 2s, we got 2p, we're up to 2, 4, 6, 8, 10. Now we're going to go
3s.
3s. 2, 4, 6, 8, 10, 12. And then 3 more.
2d.
One second. So we got 2, 4, 6, 8, 10, 12 out of space. Let me erase this. Uh, 2, 4, 6, 8, 10, 12, and now I need,
3 more.
let's see, we're in 3s, now I need 3p. Right? I need 1, 2, 3. I'm going to go here, here, here. Okay. Okay, and so what we're going to do at this point is we go, our hybridization, we're going to go 3s, p, 3, d, right? So we're going to borrow from one of the d that we do not actually have up here. We're going to put one up there. Okay, has, you know, we're in the third shell, or third principal energy level, so there are d orbitals even though we don't have one in it. And so what happens here is, we'd be at the tippy top, right? And how many orbitals are we going to have?
5.
1, 2, 3, 4, 5. And so we'll have 5 of these. 1, 2, 3, 4, 5. Right? And each one of these is going to get 1. Okay? And so when we have that, what shape is that going to produce? Trigonal bipyramidal.
Yeah.
Okay, so that's going to look like, we're going to come out here, right? And we're going to go up, we're going to go down, and we're going to go back, right? We're going to come out here, and we're going to go back here, right? 1, 2, 3, 4, nope, that's not right. That's not right, that's the octahedral.
Go one extra.
Let's try that again. Down, up,
Forward.
out. Yeah, this is it. Okay.
Back and
so 1, 2, 3, 4, 5. All right, very good. Okay. You know why it's called trigonal bipyramidal?
Forms like 3 pyramids there.
One there, and then you get another one that comes down here. All right. Okay.
Diamond shape.
Pardon?
Like a diamond shape.
Yeah, something like that. Now let's do the next one. All right. So now our next one is going to be SP3D2. Right, and so which one do they want us to use for this one? SF6. All right, topping out for sulfur.
16.
16, so just one pass where we were. I'm going to start much lower this time. We're going to go 1S, we're going to go 2S, we're going to go 2P, we're going to go 3S, we're going to go 3P. Now how many do I have here?
In 3P?
You said I have 16?
Yeah.
Okay, so 1, 2, 3, here. Is that right?
Yeah.
Okay. All right. And of course I have my 3D, which are unoccupied. And we're going to hybridize to here. We're going to go 1, 2, 3, 4, 5. We're doing we're doing SP3D2, so you count them, that's 1, 2, 3, 4, 5, 6. So I need 1, 2, 3, 4, 5, 6. So these are my SP3D2 orbitals, and I've got 1, 2, 3, 4, 5, 6 of these things. And my shape is the first one that I drew. I've got 2 of them coming out of the plane at me. And 2 of them going back, right? These are in a plane. These, sure I am supposed to put 3, aren't I? No, I don't have to put the little one. Okay. So it gives you some rules for doing these, okay? Let me switch to a different marker because the black ones are just dead on me. All right, so number 1, determine the Lewis structure. Number 2, determine the regions. Give me 1 second. I need to tell you why we're putting these rules. Let me do that. Number 1. All right, so this is assigning hybrid orbitals to central atoms. Hybridization of an atom is determined based on the number of regions of electron density that surround it. The geometrical arrangements characteristic of various sets of hybrid orbitals are shown. These arrangements are identical to those of electron pair geometries predicted by VSEPR theory, and VSEPR predicts the shapes of the molecules. And hybrid orbital theory provides an explanation for how these shapes are formed. To find hybridization of a central atom, use the following guidelines. So, number 1, determine the Lewis structure. Number 2, determine the number of regions of electron density. Using the VSEPR theory, in which single bonds, multiple bonds, radicals, and load pairs each count as a region. Number 3, assign the set of hybrid orbitals that corresponds to this. Assign the set of hybrid orbitals from figure 8.21 that corresponds to this geometry, which is figure 8.21. So we're going to do this, right? It's kind of one of the end goals of all the work that we've been doing so far is dealing with this. Ammonium sulfate is an important fertilizer. What is the hybridization of the central sulfur atom in the sulfate ion? SO4 2 negative. Okay. All right, so let's do SO4 2 negative, right? So sulfur, right? Wants us to begin with Lewis structure. So how many valence electrons does sulfur have?
6.
6. So 1, 2, 3, 4, 5, 6. All right, I've got 4 oxygens. So here's an oxygen. Here's an oxygen. Here's an oxygen. Here's an oxygen. All right. Okay. Now I've got oxygens that are unsatisfied, right? Because each of these right now looks like this. Right, so oxygens, none of these oxygens are satisfied, and I also have 2 more electrons to account for. So I can take care of this by double bonding this one, right? And by double bonding this one, I need to steal an electron from here to do that, right? Sulfur satisfied, right? Oxygen is seeing. These 2 are satisfied, these 2 are not, right? So they're each gonna, but that makes sense, it's -2 because they're each gonna pick up 1, right? So that puts this as a negative region and that as a negative region, right? So now right now, our next, so we've determined the Lewis structure. Next, determine the number of regions of electron density. How many regions of electron density do we have?
4.
We have 4, right? So which shape is gonna correspond to that? tetrahedral, right? So it'll be sulfur with something like this. Right? And so this will be bonding with an oxygen, bonding with an oxygen, bonding with an oxygen, bonding with an oxygen, negative, negative. Well, that should be good. Okay. Good, good. All right, let's try another one. By the way, oh, we didn't, you know what we didn't do there? The question is, what's the hybridization on the sulfur? So we need to go back and we need to look at that. We did find its shape, which is good. What we didn't do is find its hybridization. So sulfur has how many total?
16.
16, right? So you're looking at S1 having 2, S2 having 2, P2 having 6, and then S3 having 2, and S3 or P3 having 4?
Yeah.
4, okay. All right. What kind of bond is this?
It's a sigma.
It's a sigma. And this?
Sigma.
Sigma, 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 pi, pi. Okay, so I've got 4 sigmas and 2 pi's. What's true of pi bonds? What's true of pi bonds? What shape can make pi bonds?
It needs to be the P.
Has to be a P, can't be a hybrid, it's got to be a P, right? So I've got, when I look at this, I know I've got 2 pi bonds, right? Which means that I've got to have 2 p orbitals, or p subshells, right? And I've got 1, 2, 3, 4 of the sigmas. So I've got 4 sigmas, which those are going to be of 4 sp hybrids, right? Okay? So that's going to come from here, right? 2 of these p's, I'm going to kind of redraw this. I've got S3, right? I've got 1 of those shells, and I've got P3, and I've got 1, 2, 3 of those shells, right? And they should have 1, 2, 3, 4. Now, I need 2 of them, right? So I need 4 of these total, right? So I need, this is going to be S, P, 3. It's got to be 3, right? So 1, 2, 3, 4. Let's confirm that that's what they have. They have it as SP3, so that's good. All right, let's do the next one. Give myself more room. All right. Let's just do SEF4. Let's try that one. SEF4. Atomic number for selenium?
34.
34. How many valence electrons?
6.
6 valence. 6 valence. Okay. Atomic number 34. So I got 1 S2, right? 2 S2, 2 P6, 3 S2, 3 P6. Is that right? I'm going to go to 4 S2, and then 3D. How many? 2, 4. That's 10. 18, no, I'm sorry, 2, 4, 10, 12, 18, 20. This has to be 3d10, right?
Yeah.
That'll get me to 30. I need to get more. So now I'm at 4p4, right? Okay. All right. Well, that tells me that I'm dealing over here with 4s. And I'm dealing with 3d. And I'm dealing with 4p. Everything's good?
Mm-hmm.
Okay. Now, bottom line though, I'm dealing with how many valence electrons?
6.
6. So we do selenium. We're going to go 1, 2, 3, 4, 5, 6. And it is bonding with how many fluorines?
4.
4. Right, so F here. F. Right. Okay. All right. I have no pi bonds. I've got a couple sigma bonds though, right? How many sigma bonds do I have?
4.
4. Now, the reality is, it's not going to go the way I've drawn it here.
You're going to have a pair
I'm
of
going to have a
legs.
pair. So I'm going to go ahead and I'm going to put these back. I'm going to draw it this way. Sigma bond, sigma bond. Okay. So I've got 4 sigma bonds and 1 pair of unbonded electrons, right? So I need 4 of these things, and yeah.
You're going to use the 4s and 4p to do that?
Okay. These guys, we're just going to leave how they are. Okay. So I'm going to use my 4s, right? And now I need P, I have 3 of those, I need 3 of those. So I'll use all 3, 1, 2, 3. And now I need, because I need to fit 4 of these and I only have 3, I need a D, right? So I go here.
You still get a D even if it's full, because it's one above the 4.
Oh, this is SP. I'm sorry, say it again?
You would get like the 4D to do that because you need to
Yes.
keep that.
Yes, yes, exactly, because I only have 2 of these. You ever feel out of your league? Just a hair out of your league? Maybe that it's using all 3 of these and kicking 2 up, and I don't have a box for that in my brain.
It's kicking the
Because
one.
I don't do this very often, I haven't done it in 10 years. And they don't give any explanation. Let's look at it.
Because I think you would go, because there's a 5S before the 5S, 5P, then 4D, you know?
Let's go look at this.
Yeah.
Let's go SP3 hybridization. Oh, SP3D. And SEF4, is that right?
Yeah.
Okay.
Welcome to Aurora.
Oh,
Thank you for jumping on. LCM, simple formula, PC plus PC by 2.
I'm not gonna be able to understand when we get out here. Let's find the, see what this guy is.
Let's describe the bonding and the shape in SEF4. In order to do that, you need to start with a good Lewis electron dot structure. So you have to be very good at drawing your Lewis electron dot structures. Here's SEF4, and what I've done here is I've drawn the Lewis electron dot structure, and then I've suppressed all the electrons around the fluorines because they're kind of getting in the way here. And what we really need is the steric number around selenium. So that steric number is 1, 2, 3, 4, 5. I have to accommodate 4 fluorines and a lone pair for steric number 5. Once I have the steric number, I can get to the geometry. It also gives me the hybridization. So steric number 5 means I'm going to use 5 equivalent hybrid orbitals. They're going to come from the 5 standard atomic orbitals, d, s, and 3 p's. The VSEPR arrangement for 5 things is trigonal bipyramidal. It looks like this. So our trigonal bipyramidal arrangement, but in this case when we go to the molecular shape, we ignore electron pairs. So we always name our shapes without the electron pair. So removing that electron
Seesaw.
pair gives me a shape that looks like this, a little seesaw. So there's an electron pair here, but the molecular shape is named just by the atoms. So a seesaw configuration, and I'll have 2 bond angles. I'll have a bond angle of 180 degrees and a bond angle of 120 degrees.
He's not helping me out.
So
He's not answering the question at
120
all, is he?
Yeah, I didn't explain where did it came from.
I don't think we're getting an answer, really. All right, we're going to move on because it's not going to be worth it. All right, let's keep going.
Yeah, I understand that it's gonna be a SP3D,
Yeah.
but from what
Yeah, it'd be nice to.
I understand from where it comes, but
Yeah.
it's alright.
Where'd my spray go? There it is. Okay. Let's do another one. Urea, NH2, C, O, why it's, I guess I'm not sure, NH2 is sometimes used as a source of nitrogen in fertilizers. What is the hybridization of the carbon atom in urea? So we got to start with the Lewis structure of this. Okay, so we're going to have carbon, right? It's going to bond to a nitrogen. The nitrogen's bonding to 2 hydrogens. Let's see. Nitrogen has 5, so 1, 2, 3, 4, 5. Right, so it's bonding here and it's bonding here. All right, 1, 2, okay, now we're going to bond here. So 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen's happy. Okay, now over here I got another one just like that. Right?
And
Okay.
double bond with oxygen.
Is that what's, is that That is a weird way to represent that. But so be it. So now we're going to double bond with oxygen. Okay. All right, now what is the question? Right there. What is the hybridization of carbon in this atom? Okay. So we've drawn our Lewis structure. How many regions of electron density do we have?
3.
We have 3. Okay. And so when I do 3, what's my molecular shape going to be?
Trigonal planar.
It's going to be trigonal planar, right? So we're going to have not a problem. And what hybridization gives me trigonal planar?
I think it's sp2.
Should be sp2, right? It's going to account for this. So we'll just double check. And it likes sp2. Easy. Okay, let's do one more, and then we'll look at some other things. Okay. This time it wants us to do acetic acid. Okay, for acetic acid, we want H3CCO. Just doing the thing again, letting us know it's double bonded, OH. Okay, so here's my central carbon atom, right? So I can see right away, I know that it's double bonded to an oxygen, so I'm going to go ahead and do that. I know it's bonded over here to an O, which is bonded to an H, right? An oxygen satisfied. And over here, I'm coming to another C, and this one has everything's coming off of it. And so I got the same shape, trigonal planar, right? And so I got 3 regions that should be sp2. And the answer is sp2. Okay? Not a problem. Now the next one, multiple bonds. By the end of this, all right. The hybrid orbital model appears to account well for geometry of molecules involving single covalent bonds, and also capable of describing molecules containing double bonds and triple bonds. We've already discussed that multiple bonds consist of sigma and pi bonds. Nick, we consider how we visualize these components and how they relate to hybrid orbitals. Lewis structure for ethine, C2H4. Right, so start with this, right? Each one of these is going to get 2. Satisfy the octet rule, I need a double bond right there. All right. Each carbon atom is surrounded by 1 other carbon atom and 2 hydrogen atoms. The 3 bonding regions form a trigonal planar electron geometry pair. So I got one kind of that I'm looking at here. It's trigonal planar, 3 regions, and I got another one over here. I'm also looking at this trigonal planar. 3 bonding regions form a trigonal planar geometry pair. Thus, we expect the sigma bonds from each carbon atom are formed using a set of. Okay, so let's look at what.
sp2.
Yeah, so this is a sigma bond, sigma bond, sigma bond, sigma bond, sigma bond, pi bond, right? Okay, and so whenever I have this shape, that has to be sp2, right? And so this sigma bond has to involve an sp2 from this one and an sp2 from that one. And then the pi bond has to come from?
Yes.
No, from the P.
Yeah.
Yeah.
Oh, the P.
Yeah, 2p. Okay. All right. These orbitals form the CH single bonds and the sigma bond of the carbon-to-carbon double bond. Pi bond in the carbon-to-carbon double bond results from the overlap of the third remaining p orbital on each carbon atom that is not involved in hybridization. This unhybridized p orbital is perpendicular to the plane of the sp2 hybrid orbitals. Thus, the unhybridized 2p orbitals overlap in a side-to-side fashion above and below the internuclear axis. What is the point with all this? What do they want you to know? They want you to know what this looks like. So we can visualize what this is going to look like. I know it's trigonal planar, right? So I can draw it like this. Right, here's carbon, here's hydrogen, and it's going to form a sigma bond. You know, of course, these are doing this, right? I'm going to overlap with another one, with my carbon. Here's my hydrogen, it's going to overlap, hydrogen's going to overlap, hydrogen's going to overlap, one more up here, right? Okay, so this is where these are going to overlap, but of course this is a, we got one more that I can draw, right? And so it's a pi bond, and so it's going to be P. I'm just wondering if I should have drawn this differently than I did. How did they draw it?
I think he's like.
Let me start this over just a little bit. Carbon. Yeah, that's where I made a mistake. Okay, let me take this out. Let me not use this one. Draw it here. Now that leaves me room to go ahead and do my pi bonding up here. So I've got my pi bonding coming in and out of this plane, essentially. I'm doing this thing.
Like he did on the video.
Yeah.
Like he goes over the
Yeah. Okay.
stuff to draw.
Very. Oh my goodness. That's a nightmare to draw. Let's try this next problem. Fortunately, glad to get to gas laws next. Back to the math. Okay. Some acid rain results from the reaction of sulfur dioxide with atmospheric water vapor by the formation of sulfuric acid. Sulfur dioxide is a major component of volcanic gases as well as a product of combustion of sulfur-containing coal. What is the hybridization of sulfur in SO2? We didn't need all that. You just had to ask me what SO2 was, right? So we want to know what S hybridization is in SO2, okay? All right, so how many valence electrons in sulfur?
6.
6, right? So 1, 2, 3, 4, 5, 6, and we're doing 6O2, right? So I'm going to go oxygen, and I'm going to go oxygen, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I need a double bond right here, right? So I'm just going to snatch one of these. And I need a double bond right here, so I'm just going to borrow those, and that leaves me with one lone pair. So how many regions do I have?
3.
3, right? 3 regions. So this should be
And
what hybridization is going to give me 3 regions? And right on the bent though. That's good.
it's SP.
SP 2, right? SP2. It's got the 1, 2, 3 has to add up to my 3 regions for that. Good.
Yeah, so you count the electrons.
Say it again?
I was counting only the 2 oxygens. I didn't count.
Oh,
the
yeah,
pairs.
no, these still count. Good.
Okay, you count the regions.
Yes.
positive.
Yep, that's exactly it. Good. Okay, let's move on. What time do we have? Not much.
Around 20. Yeah, 20
Not
minutes.
much. Okay. I'm going to show you a video. And I might show you the video again next class.
It's alright.
It'll be good. All right.
Are you struggling in your calculus class? Are
Yeah.
you having a hard time
I
understanding your
get
instructor?
this
Do you
announcement
wish
all
there was
the
a simpler
time.
way? I get it.
Okay, welcome everyone. This is Professor Davis again, back to talk to you this time about molecular orbitals. I'd like to begin this discussion by considering 2 individual hydrogen atoms, which are depicted here as white spheres. Now, we already know from our discussion on atomic structure that each of these hydrogen atoms should have a 1s subshell containing a single electron. Now, the 1s subshell is really a probability density function of where we might find an electron located in space at any point in time. They don't really move in circular orbits the way I've shown them here, but this is the easiest way to convey that the electrons are in motion within that volume of space. Now, when these 2 hydrogen atoms get together and form a chemical bond, something happens to those 1s subshells. They merge and form what's known as a molecular orbital, or more accurately, a molecular orbital system, consisting of 2 different regions of space. The first molecular orbital is called the sigma molecular orbital. You'll notice that the sigma molecular orbital contains a great deal of density between the 2 nuclei, and therefore electrons which may populate this orbital are likely to be found in between the 2 positively charged nuclei, screening them from one another, and thereby stabilizing this molecule. The second molecular orbital which forms in this system is known as the sigma star. You'll notice immediately that the sigma star molecular orbital contains very little electron density in between the nuclei. And in fact, placing electrons in this location in space does nothing to stabilize the molecule. If anything, it actually will destabilize the molecule by pushing the 2 positively charged nuclei closer together through electrostatic repulsion. So when we work with molecular orbitals, we need to keep a few rules in mind. The first is that the number of atomic orbitals which go into the system is equal to the number of molecular orbitals which are formed. The second rule, molecular orbitals fill from lowest to highest energy following Hund's rule and the Pauli exclusion principle. And finally, bonding between any 2 atoms will only occur when there is an energetic advantage to populating the molecular orbital system when compared to the atomic orbital system. So now that we have a rough understanding of what molecular orbitals are, and
pause there. I do think we want to have this, okay? All right, so number 1. number of atomic orbitals that go in will equal the number of molecular orbitals that come out. Number 2, slightly different color this time. Number 2 is that molecular orbitals fill from lowest to highest. Following Hund's rule and Pauli exclusion. Okay. And number 3 is bonding only occurs when there's an energetic advantage. Okay. All right.
The rules that we need to follow to predict how they'll behave, let's take a look at some specific, simple molecules and see if we can explain their behavior using molecular orbital theory. So let's begin by considering the molecular orbitals of a hydrogen molecule, like the one that we looked at on the earlier slide. Here I've depicted on an energy diagram the atomic orbitals of 2 separate hydrogen atoms. Now, I've placed one electron spin up and the other spin down, simply for convenience sake, but they could be in either orientation at this point. So let's take these hydrogen atoms and combine their 1s subshells to form the new molecular orbital system. Now notice that in doing so, I've created the sigma molecular orbital, which is of lower energy, and the sigma star molecular orbital, which is of higher energy. So as I populate this molecular orbital system, using my allocation of electrons from my atoms, I'll begin with the sigma and only fill the sigma star if needs be. As you can see, I use my entire allocation of electrons in filling the bonding orbital. So in this case, the energy of the system overall has decreased. This means that there is an immediate energetic benefit to bonding. Furthermore, I can calculate the order of the bond simply by taking the number of bonding electrons, subtracting the number of antibonding electrons, and dividing by 2, of course, to acknowledge that there are 2 electrons involved in each chemical bond. So in this case, I have 2 bonding electrons in the sigma molecular orbital and 0 electrons in the antibonding sigma star. Placing these numbers into my equation allows me to predict that my hydrogen molecule will be joined by a single bond. And this is in fact the case. Now let's take a look at another example of a very simple molecule. In this case, we're going to work out the molecular orbital systems of a helium molecule consisting of H2. Now we all know that this isn't really how helium behaves. And what we're going to do now is demonstrate that there's no benefit for a helium atom to bond. So we have our 1s subshells on our energy diagram, each populated with 2 electrons, just as a neutral helium atom should be. Let's create that molecular orbital system now. There's my sigma and my sigma star molecular orbitals. But now, if I populate them, following Hund's rule and the Pauli exclusion principle, going from lowest energy to highest, what I notice is that while I place 2 electrons into a bonding orbital, I'm forced to place my other 2 electrons in the higher energy antibonding orbital, canceling out the energetic benefit. This is easy to see in my calculation of bond order, in which I have 2 bonding electrons, but also 2 antibonding electrons, canceling them out. Therefore, the net bond order is 0, meaning my prediction is that helium atoms will not bond to one another to form a diatomic molecule. So now that we've looked at 2 very simple examples, we're ready for something a bit more complex. Let's consider the molecular orbitals of a nitrogen molecule, N2. We all know from our discussions on atomic structure that a nitrogen atom should have an electron configuration of 1s2, 2s2, 2p3. It is the 3 electrons in the p subshell which will be participating in bonding during this discussion. So let's place that 2p subshell in our energy diagram and populate them as they would be in nitrogen atoms. Again, in this case, I've placed certain electrons spin up and others spin down simply for convenience. They could be in either spin orientation at this point. Now let's combine our 2p subshells and see what happens. You'll notice that when we do this, we get the expected sigma and sigma star bonding and antibonding orbitals, but we also have the possibility of pi bond formation now. The sideways overlap of the 2p orbitals from our 2 atoms create 2 pi bonding orbitals and 2 pi star antibonding orbitals of equal energy. Now let's populate this system using our allocation of electrons from our nitrogen atoms. You can see clearly in this case that all of the electrons have made their way downhill energetically into bonding orbitals. And furthermore, I can calculate the bond order of nitrogen molecule in the usual way. I have 6 electrons in bonding molecular orbitals, 0 electrons in antibonding molecular orbitals, meaning that when I run my calculation, I can predict nitrogen will have a triple bond. And of course, this is the case. Finally, let's take a look at one more example. How about a molecule of oxygen? Oxygen atoms have an electron configuration of 1s2, 2s2, 2p4. So we'll treat them similarly to the nitrogen example, except that each of our subshells now has 4 electrons. Just as before, I'll create my molecular orbital system by combining all of my 6 p atomic orbitals to form 6 molecular orbitals. As I populate them, notice that I have 6 electrons moving into bonding orbitals, but that I'm left with 2 additional electrons with nowhere else to go except into an antibonding orbital. You'll also notice that because I'm following Hund's rule and the Pauli exclusion principle, these 2 electrons go into individual pi star orbitals. The consequence of this should be clear, that the bond order of oxygen is determined by its 6 bonding electrons, but also its 2 antibonding electrons. Therefore, we would expect the bond order in oxygen to be 2. Not only that, but we expect oxygen to behave as a paramagnetic species because it contains 2 unpaired electrons in its antibonding molecular orbitals. And both of these are in fact the case with oxygen. And this concludes our discussion of molecular orbitals for now. I'll see you on the next installment.
My wife emails me order.
My goodness.
Let's do a little. See what we can do. Come over here. let's do boron. Atomic number?
5.
5. 1s2. 2s2. 2p1. Okay. All right. I'm not going to be worried about this. We know, right? Okay. Now am I confusing myself? He did oxygen and he did nitrogen. Those were, he ignored them. They fill up certainly more than the 1p. According to his deal, we're going to ignore the S2, right? We're going to go to 2p. We go 2p, right? And at this point, we would produce hypothetically, do something like this, right? All right. I'm going to drop it here. I'm going to make sure I'm not in over my skis. We'll come back to this next class. What is the date today? Wednesday? So we'll come back to this on Monday. All right. We'll pick up here on Monday.